Hello guys, today we're going to cover two main things, how to declare arrays in two ways, and another thing we're going to take the LittleEndian, BigEndian, which is how we store data in memory. And first I want to give you the arrays, because it will help you better to understand the LittleEndian and BigEndian. Let's say I have include a1, and now we want to declare an array 32.inc and data. We have two ways. First way, let's name it list, and I can say define word or word. And if it was signed, if you wanted it signed, I could say sign word. A good question is, I'm not going to answer it now, I'm going to leave it. Word takes a negative value. If I give it -7, it will take it. So why do we use sign word to represent negative values? Like now, if I say this equals -7, it's good. If I say list word as sign word, declaring it as a negative, so it can take. This is also possible. The question is, what's the difference between them? If I can put -7 here in word, why do I have sign word? I'm going to leave the answer to you guys. I'll answer it next time. Think of it. I think it's hard to find an answer online. But let's say sign word, and let's put 1000 hexadecimal. Those are 1 byte, and those are 1 byte. And I can say, let's put it 64 70. Let's put 70. This is decimal, remember, by default. And I can do this and assembly. And this is 1 byte. And I can say binary. I declared a list or an array of 3 elements. First element, this one. Second element, and third element. I can also declare, let's say, list 1 and say find byte or byte, and I want to change it there. And let's say, no, let's make it a word double. Word is 2 bytes, double word is 4 bytes. So let's go 1, 2, 3, 4. 1, 2, 3, 4 bytes hexadecimal. And let's do 1, 1, 2, 3, 2, 3, 4, 4 hexadecimal. An array of 2 elements. And we also can define array using what's called the dub operator. The dub operator takes the size. Let's say I want an array of size 5 initialized over 2 zeros, or uninitialized, or I can say 10. But let's make it array, but we didn't give it the size. And let's say byte, so that's 0. And I can say array 1 byte, and I can say 1, 2, and 4 dot an array inside an array. Don't think this is a two-dimensional array. I'll explain it in a minute. And let's say 1. What this is an array of 1, 2, 3, and 1, 1, 1, 1. Those are the 4 ones, and those are the 2. So an array of size 6. Both of those, an array of size 6 element, and we have 6 bytes. This is the data. Should make one of those a small array, no problem. So now dot code, and let me draw the memory of this one so we can understand it in a better way. Best we can get it to table. I have here a word 2 byte. I have 6 bytes. Here I have 8 bytes. That's 14. 14 and 5 bytes. That's 19. 25. So I'm gonna have 25. Oh, and let's make them 2 columns. But I'm just gonna show you it's only 1 column. Let's fix this first. Then go back to that one. And let's say this takes the address. And this is the memory. And let's say you're gonna see different things. You can start from here. Let's say address 0x0000, for example. Or we can start from bottom and go up. This will be address 0x0001, and let's assume this is byte addressable memory. Byte addressable memory meaning each byte has an address. Each of those is a byte. If I had a word addressable memory, each word will have an address, meaning every 2 bytes will have 1 address. Byte addressable memory, every byte has an address. Word addressable memory, every 2 bytes have an address. And this would be 0x003. This is 4, 5, 6. I just want to show you 7, 8, 9, 10. We'll add the rest later, but let's see this. Now let's see, we're going to start with address 000. What do I have? Now the LittleEndian kicks in. The LittleEndian kicks in when I have more than 1 byte in a byte addressable memory and more than a word in a word addressable memory. Meaning, how am I going to save this? The 1000 hex. Am I going to say 1, 0, 0, 0, 0? And why is that? That every 2 digits, those 2 digits are a byte, and those 2 digits are a byte. The 0, 0 is a byte, and the 1, 0 is a byte. And this is a byte addressable memory, so every, let's say, here every place takes a byte. LittleEndian. How memory is stored, LittleEndian and BigEndian. This is BigEndian. LittleEndian, which we're going to cover, and many other architecture is sorry guys. LittleEndian, and it's with an E, not with an I. The most significant byte, the lowest significant byte at the lowest address. So this is the way how it's stored. This is the first element. This is, let's give that color. This is the first element. LittleEndian. How do I know least significant byte? The right one has the lowest value. Remember when we did the convergence, we always started from where? We started with 1, 2, 4, 8. So this bit has the lowest value, 2 to the power 0, lowest value, 2 to the power 1, 2 to the power 2, 2 to the power 3. So when we go left, the value increases. So for those 2 bytes, this is the least significant byte. This is the high significant byte. So the least significant byte at the lowest address, which is 0, 0. Now the 70, we convert it to binary. This is going to be saved in binary, but I put it in hexa. 70, if I wanted this in binary, what will it be? It's going to be, let's say we had, 1, 2, 4, 8, 60, 32, and 64. And each of those, this is a bit, remember, this is converting decimal to binary. And we took this. So here I have 1, 2, 3, 4, 7 bits. I'm going to have the 64, 7 bits, and we can say 1, 0, 0, and 0, and 1, 1, 0. This is binary. This is binary. So now we have 7 bits, and we have it as this array as words. So 2 bytes, 2 bytes, 2 bytes. I'm gonna have what? 7, 9 zeros here. So this is how many zeros? 1, 2, 3, 4, 5, 6. Least significant byte at the lowest address. Least significant byte at the lowest address. So 0, 1, 1, 0, 0, 0, 8, 68, 264, 1, 2, 4, 8, 0, and let's put those hexa, and you know how to put those in binary, and this is 0, 0, 0, this is another, and this color. This is the second word. Then what do I have here? Then I have this, so I'm going to put those. Least significant byte at the lowest address, LittleEndian. So it's going to be 4, 0, 1, 1, 1, and then I have 1, 0, 1, 1, 1, 1, 1, and this is the third element of the array. This is the memory of the program. Let's see what do we have. Then we have a D word. D word takes 4 bytes. So it's going to take those 4. And I'm going to say the least significant byte at the lowest address. So it's going to be 78, 56, and this is hexadecimal, guys. You can convert it to 34 and 12. Here I have 1 1 2 2 3 3, and I don't know. Let's see, that's 4 4 hexes. So I'm gonna have 4 4 3 3 and 1 1. What that? Okay. So this will be my this is my secondary array. And let's say here we're gonna have a list. That one, list 1. Here we're gonna have list 1. This is 11, 12, 13. I don't care about those addresses. We're gonna see why. Now I have an array of 5 bytes. So think of this as an array. 5 bytes, and we declare them all as zeros. So we're gonna have 5 zeros. 0, 0, 0, 0, 0. Then we're gonna have 1. 1, 2, and 4 ones. 1, 2. Exactly, and this was array 1. So we took how to do LittleEndian, how to put the values in memory, and we took how to declare arrays of 2. One way is this, and the other way is using the operator. We have another thing, and let's say I want to find the size of this array. I'll say size equals $sign is called the current location pointer, and minus list. And let's look at my memory. And remember, it's going line by line. So we did this, now it's going to size. Current location pointer will be waiting here. Will be waiting here. It filled those, and it filled this, and now it's waiting here. Current location pointer. So it will be at address 6. Address 6 minus list, which is what? 0. Address 0. If you think of the address 0 and address 6. So this will give me what? 6 minus 0, and this will be 6, which is the number of bytes in the list. Number of bytes in the list. To find how many elements I have, I divide it by word, which is 2 bytes, divided by 2, this will give me read. So I can say size equals $ minus list, the name of the array or list, divided by the word. If it was a double word, I'll divide by 4. If it was single bytes, I divide by 1, which will give me 6 elements. And we're going to need those for what? For loops. We do, because you know arrays, we're going to need loops. And here I'm going to say, let's go back to the memory and look at the memory. I have list 1 at address 6. So let's say size 1 equals $current location pointer minus list 1. This is going to give me this one at 6, and let's see what's the current location pointer after inputting this. It's going to be address 14. Current location pointer here. Fill the 11 and it's waiting here. So it's going to be 14. Oops. Minus 6. Total of 8 bytes, the size of the array, divided by 4, which are this type of the array gives me 2 elements. We have 2 elements in this array. 2 elements in this array. And this, the assembly, those are comments. This, the assembly. Now what happens if I we wrote this, and then I took this and put it here. It's going to do $, which is going to be after filling all this, which is going to be on address 26, minus list, which is going to be address 0. So it's going to give me the whole memory. So be careful. After declaring each array, I calculate the size of it. Here we have 4, so I can say here, this one we don't need to do it, it's 5. Here I can say size 2 equals $, and I'm not going to do it, you go check it, minus array 1, and this will give me the size of this array, which is 6 bytes. 6 bytes. Now let's do this main process, and I do exit and main end process and end main. Now a really important thing to learn. Let's say if I want to add list 1, and here this is how we're going to use the index. Move, I'm going to say 2, I'm going to use EAX because I have a D word. If I wanted to do list, which is this one, I use AX. If I wanted to do this one, and we'll show you AX, and I move list 1. List 1 is the first element. This one. It's actually list 1 plus 0. But we don't care about 0. And then I say add to the accumulator, which has list 1, which is the first element, which is this. Add to it this. Add list 1 plus 1. Is it plus 1 or no? No. Okay. Bytes. Go back to memory. That's why drawing the memory is going to be really important. This is list 1 plus 0 plus 1. plus 2 plus 3 is going to be plus 4. So because it's a new word and we can do it this way. Either this way or that way. And let's see the registers. So we can down reg report and I don't want to have the elements here because it's going to be, I don't want to do those because I'm doing it that loop. It's going to, let's change the size of this to just for now, just so do this. I just want to show you how to. And I just want to see them in the registers. I don't want to see them. So here I'll say add or move. I'm going to move the first element, which is what? 1. And I prefer clear, but let's see if I want to clear here. EAS, but let's leave it there. Move to AL. Why? Because it's 1 byte. My array is 1 byte. And I'd say array 1, which is the first element. Then I'd say add to AL array 1 plus 1 because it's a byte. If it was a word, I'd say array plus 2 AL array, and we're going to take how to do it in loops. I just want to show you this so you can understand it better. Plus 2 is going to have 2 add AL, and I'm going to have array 1 plus 3 add A. Oh, that's 1, 1, 2. Okay, that's good. From here. So show me the registers. And guys, it's really important. I want to do something here. I'm going to move to AX. So, or let's move this, but I want to move it from list 1. So if I said list 1 minus 1 is this, minus 2 is this, minus 3, minus 4, minus 5, minus 6. Let's put list 1 minus 6. See, going in reverse order. Minus 6, and remember we can do this. Hopefully this works. I have it done. Curl down register, and we're done with this. Let's save it as program 6.assembly. Let's see programs. Tools. Line 3. Line 6. But let's fix line 3 first. So now they want to the favorite now to evaluation. to disconnect find a way to generalize size here. Size. Let's see if I can find them here. That's what the problem. I think we need to use the put directive, but let's see if this works. Error sentence, error size. Size 1 simple. Symbol find it. So it's just not like size, so what but make it size 3. This way. Okay. Doing like the word size is a reserved word, so we got the word there. Instruction operands must be the same size. Error line 18. Lines. So what we have this one keyword. No. Find out the word. Just to get out the word actually. Load it as a double word, so this is the word. So that's good. So that problem. Let's see if we have another problem. Instruction operands must be the same. And the key is 1 minus 6. So it's the word. So let's take this one as okay, and let's check. I don't know if you can see this, but try to zoom. Now that's a problem if they want to buy the another buy. This zoom again. So let me tell you the first one. EAX has a value of 1, 2, 3, 4, 5, 6, 7, 8. And that's right. This one, this one. And now we're adding a list one, this plus this in hexadecimal. So let's see what the result is. It's going to give me C, 4 and 8 is 12. Give me C, B, 4 and 7 is 11. And 3 and 6 is 9, 9. C, B, and I'm reading it from right to left. C, B, 9, 8, 6, 5, 3, 2, 3, 2. Copy it. I can't paste that down. Okay. Anyway, I'll read the output, and I'll have a screenshot. I'll add it to the description. And we can do print screen. So now we're doing, let's say, move AL, array 1, which is this one, by to AL, which is 1. And I told you we might have a problem. We need to do move EAX 0. So we move EAX 0. I left it. I told you I have a problem, and we got that problem. So size, pull up, okay. So, so this is not working. So let's do this. Let's run. And here we added the 1. This is the 1. And 1 here. Then we add the second one to it. Was it 2? 2. And then we have 1 more. So it's a 3, 3, 4, 5. And then right. 1, 3, 4, and 5. For long registers. And then what we did is we went here, list 1, and went to this. This one, I'm not sure it's going to give us the right one, but let's see. Now it gave us the right one. 5,000 exits. The 4.6 they came from another. Don't worry about the 4.6, but they gave us the it's from the previous but so this is mainly arrays in 2 ways. LittleEndian. Remember, it's good to practice this. It's really important to understand the memory layout. It's really important. It helps a lot, guys. It helps a lot, especially in this. And next time we're gonna do arrays and grouping of that. We're gonna take one example just to demonstrate this more on how to rearrange an array. Let's say I'll have 2, 1, 3, three numbers, and rearrange an array just to show you how it works. Okay, thank you guys, and see you next time.